So today, we're going to be deriving an equation for the speed of a wave on a string, which is under a constant tension and of a given material. What? What am I finding? So we're going to be deriving an expression that gives you the speed of a wave on a string. The expression being b being the square root of tension over mu, where mu is the linear density or the mass per unit length. Now to derive this, you need to accept the following: F equals ma. So it's also the fact that when you add two vectors, what you're really doing is adding the horizontal and vertical components. Okay, we also have the definition of the derivative. Okay, you need to understand how gradients work and how cosine of 2 pi is equal to 1. You need to understand that. So you need to do the chain rule here. You know the derivatives of sine and cosine. And finally, the definition of acceleration is the second derivative of position with respect to time. Okay, so these are our rules. It's what we established, and from those we can get to this equation here. Okay, now consider this piece of string. So imagine that it's a guitar string. So it's going to be taut under equal and opposite it's going to be taut under equal and opposite forces of tension on both ends, so it's not moving. And we're interested in this piece of string, delta x, which is, we're going to say it's a small piece of string. So if I define mu to be the mass per unit length, then by definition, the mass of this piece of string is going to be u delta x, because our length is delta x in this case. So now imagine I pluck the string, the guitar string let's say, and caused a pulse to travel through it. I'm saying this is the positive x direction, this is positive y direction. Now it's worth noting that I'm going to say that the string is moving, the pulse is moving to the right, just because if that's a positive position, that's going to be the positive velocity direction, which will make things easier. So positive, moving to the right. So let's now find this piece of string on here. So I'm going to say it's here. So the distance between these two ends is going to be, of course, delta x. Since it's a small piece of string, we don't want a progressive wave. Particles only really move up and down. They don't move left and right. So that means the resultant force in the x direction is 0, because it's not moving in the x direction. But we know there's a force of tension as well, so you can say the tension's still there, but it's still equal and opposite. Yeah, Ft, tension. But you know when you have a pulse that delta x is going to be oscillating up and down. And let's just say it's an entire progressive wave. So it's just a wave that keeps going. That piece of string is going to move up and down constantly, which means there's going to be two forces acting on it. There's going to be an accelerating force and a restoring force. Because as it approaches the top, it slows down. And then as it goes down again, it speeds up, and it slows down again, and so on. So there's going to be two forces, one accelerating, one decelerating. They balance each other out, but they're not equal. They're only opposite in direction. So I'll put one of them here. And the other one here. You might ask, why am I putting this arrow on this side and on this side? Well, because delta x is sufficiently small, I mean, you can kind of say that they are just on top of each other. But it works to put the upwards force on the right side and the downwards force on the left side, and you see why. So if I zoom in on this part here, you can see that the resultant force of F1 and Ft, by adding the components, will be a tangent to the wave. And as you know, the gradient of a tangent is nothing but the derivative, in this case, of y with respect to x. And the gradient of the tangent in this case is simply F1 over Ft, because that's where we get this resulted from. So you can say that this ratio, dy by dx, is equal to dy by dx. So it's partial derivative of y with respect to x at the point x1, whatever that derivative is at this point. By the same logic, you can see that it applies in this case too, because if I just do it here, the tangent will resemble the resultant will resemble the tangent line. So in this case, the gradient is going to be F2 divided by Ft. So straight away, what I'll do is I'll isolate F1. It's going to be this times Ft. And we said F2 over Ft is the same as the derivative of x2. So do the same logic. So yeah, F2 so you have these two forces. Now, I assign this as the positive y direction. So it's also going to be the positive velocity direction, acceleration, and force. So this way is direction of positive force. For that reason, we can say F2 is a positive and F1 is negative. So the resultant force, which may be positive or negative, will be F2 take away F1. So the net force is going to be this take away this. So I will just factor out its tension. And that's the net force on this piece of string delta x, which is oscillating up and down, right? But we also know, by this here, that's equal to the mass experiencing the force times its acceleration. So in this case, the mass, we define the mass as mu delta x times, well, you know this particle we established is only moving in the y direction, so you can just say a sub y because it's acceleration in the y direction. Okay, so we can get rid of this here, we don't need it. We have this relationship. Now, we can simplify this. You can divide both sides by tension times delta x. If you do it on the left side, tension will disappear and you'll get this expression over delta x. What I'm going to do is, I'll say, because you know, for simplicity's sake, dy dx, you can call it y prime of x. Yeah, so it's the first derivative of y with respect to x. It'll just make things a bit easier to write. So in this case, divide this by tension times delta x, you're going to get y prime x2 take away so I hope you see where that came from. Just Ft will go away, delta x goes on the bottom. Same thing here, delta x will go away, you're going to get tension on the bottom. Now, you may notice x2 is nothing but x1 plus delta x, obviously. So sub that in there. And the only way that what we've been saying about the oscillation only being up and down would be true is if delta x was a particle, a single point. So what we can do is we take the limit as delta x approaches 0, as that distance approaches 0, and it approaches just a single point on the string. But as you might notice, this exactly resembles the definition of the derivative, where our f of x is simply y prime of x. So then you can just say y double prime of x is equal to this. And the reason I just say x now is because x1 is obviously just an arbitrary point. It could be anything, so you just call it x because it's a variable. So y double prime of x, which is by definition just d squared y dx squared, that's going to be equal to this right side. And this limit doesn't change anything because there's nothing to do with x on this side. It's all just a constant and something in the y direction. And the y component is independent of x. So you just keep this the same. Okay, so now we have this. And we would write a sub y, but from this definition down here we've established there will just be the second derivative of y, position y, with respect to time. So I'm going to rewrite that as and what we've done is we've established that this rate of change is directly proportional to this rate of change by this constant. Because mu is just a property of the material of the string. The tension is something that you shouldn't change. Say in your guitar string, the tension at the end isn't going to change when you pluck it. So we found this constant of proportionality, which should always hold, but we have it in terms of forces. So now what we can do is we can find that same constant geometrically for a more pure wave, and then equate the constants and solve from there. So what we're going to do now is we're going to derive the wave equation. So imagine we have this cosine wave here. It's not an exact cosine wave because typically it's going to reset after 2 pi and its maximum point is going to be 1. But we want it to be an arbitrary wave, so it's going to have an amplitude of a, whatever that is, and it's going to have a wavelength of lambda, not necessarily 2 pi. And what we want to do is we want to find an expression that outputs a value of y, a value of the displacement, the vertical displacement along the wave for a given x, and also for a given t, because this is, we want a moving wave, because obviously in a guitar string, in any taut string, or in any natural wave for that matter, you're going to have movement as time increases. So in other words, we're looking for y as a function of x and time. So let's just say this is a snapshot at t equals 0. So we could find y as a function of x first, so imagine we just keep this wave still. And we want to find an expression that gives you this wave. So first of all, we know cosine of 2 pi equals 1. Now cosine of 0 is also equal to 1, so in other words 2 pi, well, should we write this? Cosine of 2 pi n equals 1, where n's an integer, because after every n wavelengths, in which in this case is 2 pi, the wave resets. But we don't want it to reset after 2 pi, we want it to reset after lambda. So what you can do is you can have cosine 2 pi over lambda times x, because let's just say, because say x was equal to n lambda, some number of wavelengths, you sub that into here, this and this will cancel, you'll get cosine of 2 pi n, it will equal 1 and reset. But let's say it's equal to 1, we don't want its maximum to equal 1, we want it to equal a, so we just put a at the front, So that in this example, if x equals 1 lambda, you just get cosine 2 pi is equal to 1. 1 times a is a, and you can see when x equals lambda, y equals a, so it works in that sense. So that will give you y in terms of x. And what we did is we kept t constant. So now imagine we do the opposite. Y in terms of t. What that means is you're gonna have to keep x constant. So you're gonna pick a single point, let time run, and as the wave moves, you let it go up and down. Now, so we can put a at the front for the same reasons earlier. Now here, in this scenario, we know that the wave resets after every lambda of distance. But in terms of time, the wave will reset. This will go from, say it's at this point, at t equals 0. The time for it to go here and here again, in other words, time for it to reset, that is by definition 1 period. So you can say 2 pi over t times the variable time. So then, okay, so if you wanted to have a function of y of x and t, where you pick a value of x, you pick a value of t, and it gives you a displacement, then you can add the insides of these. So now I want to say plus or minus this part. And the reason for that is because imagine t's just a number. X is something we can pick, but t is just going to be increasing constantly. This big T is just a constant. So in other words, as your clock ticks, as time goes on, this is just an ever increasing number. And you know that when you have, just imagine cosine of x plus a, as if a is a positive number, let's say a is 5, your wave is going to move to the left by 5. So this keeps increasing, then your thing's going to keep moving to the left. And if it's increasing at a constant rate, like time, then you're going to keep moving to the left at a constant rate. Similarly, if it was x minus a, where a is a positive number, then it's going to move to the right. So this here is just a number that keeps increasing. So if you want your wave to move to the right, then you're going to have x minus this, because then as this increases, it's going to move to the right. And of course the actual reason for that is because when you have f of x plus a, you're moving this axis to the right by a, which looks as though the wave is moving to the left by a. But it doesn't really matter, you don't need to know that. All you need to know is that if it's minus t, it's a right moving wave, and if it's plus t, it's going to be moving to the left. So we have this. You also want to have a phase shift phi. So let's say we had t equals 0, we had x equals 0, so you're focused on this point here. But you might not have a cosine wave at t equals 0, it might be slightly off. So you want to adjust the wave. This phase difference will act to shift the wave left or right. So say this was equal to pi. This wave would move to the left by pi. So then at x equals 0, you would have your y would be minus a in this case. It doesn't matter in this derivation, but it's worth noting. Anyway, so this is our equation. Now, for the wave previously in the pulse, in the force diagram, I wanted the wave to be moving to the right because it's positive x direction. So in this case, if I want the wave to move to the right, I'm going to have to take the minus variant for time, and as I've said. So now what we can do is you have this expression, this geometric expression of a moving wave, a progressive wave, and we know that these rates of change here are directly proportional. Obviously we won't get this constant because there are no forces involved and there's no masses involved. This could apply to a light wave. So if we find the same relationship from a different description, different constant, then we can start solving for stuff. So let's find first this nonsense rate of change. Doesn't really tell you much. It tells you how y changes with x. What does it tell you? Jesus. how the rate of how y changes with x changes with x. Anyway, so let's find that. Okay, so now we say the partial derivative of y with respect to x equals. Okay, so when you do this, we're going to say partial derivatives because this is a function of two variables. But when we do this, we're going to take t to be constant. In other words, we take a snapshot of the wave and we see how a small change in x varies with your y. Sorry, how y will vary with a small change in x. So from the chain rule, which we have here, yes, we have it here. What we need to do is first of all find your constant. You just take out immediately. You leave it, do nothing with it. Your g of x, your inner function, is this, where you're doing with respect to x, x is variable, so t is constant, phi is constant. So you want g prime first, so in other words, you want the derivative of this with respect to x. Okay, this is a constant, so it goes away. The derivative of this term with respect to x is just this coefficient. So you're going to have, well, you're going to have a at the start, because you don't do anything with the constant. This coefficient, so bring it out. And then you have to multiply it by the derivative of the outer function. The derivative of cosine is minus sine. So you say times minus sine of, I'll just call this entire inner function z to save me time. No, actually, no, it says for complex numbers, so I'll do that. Let's just say, it's a nice letter. Using Greek letters. Gamma. Love those. Okay. So we simplify that, so that's going to be minus 2a pi over lambda times sine of this times sine of gamma. But we don't want this, we want the second derivative y with respect to x, so we're going to do the same process again. Now this is just a constant, so like once again we just leave it be. So now, same thing, we're going to differentiate this inner function with respect to x. It's going to be the same constant that you bring out. So leave this here, so minus a times this, times 2 pi lambda, times the derivative of the outer function. The derivative of sine is just positive cosine, which we have down there. So it's going to just be times times cos gamma. So let's clean that up. That's just going to be minus 4a pi squared lambda squared times cosine this. Okay, camera died. Anyway, yeah, so this is our expression for y double prime of x. Okay, so I want to just note that down up here for now. Okay, so now we've got this expression, which is simply this part. Now we're going to find this rate of change here, which is just acceleration in the y direction. So it's how one particle accelerates up and down with a small change in time. So what we want now is y dy dt. And the trick is, so now t is our variable, so we take x to be constant. We're just focusing on one particle, like here, let's say, and how as time increases, it moves up and down. Small change in y, small change in t. So if you differentiate that, obviously we keep a as it is, you leave the constant alone, times derivative of this inner function with respect to t. This is constant, they disappear. This is your variable to the power of 1, So you just take this coefficient out, because the derivative of this is just the coefficient. So you just take times this piece, so it's going to be minus 2 pi over t times the derivative of the outer function. Derivative of cosine, as I said earlier, is minus sine. So use gamma again, love that out, brilliant. Okay, so it's going to be minus, the minus will cancel, so you're just going to get 2 pi a over t. And now we can, and this is just a constant, of course. So now what we do is we want the second derivative, because that's our acceleration, of course. So to do that again, the second derivative of y with respect to t, this is constant, take it out again, so you're going to have 2a pi over t times this coefficient, so it's minus 2 pi over t times derivative of the outer function, which is just cosine of gamma. Okay, so let's clean this up quickly. It's going to be minus 4 on t squared, where t is a period. Now recall, first of all, this is 4a pi squared times 1 over t squared. We know that the frequency of a wave is defined to be 1 over its period, because the period is the time it takes for a full cycle, so 1 second divided by the time of each cycle is going to be your frequency, how many waves you get per second. So frequency is 1 over t. This is, well, we'll get to that later. Anyway, we also know that frequency is equal to the velocity of a wave over its wavelength. Now there's many ways to check this. Quick way to check it is by looking at the dimensions. So this is, the unit of this is seconds to the minus 1. This is meters times seconds to the minus 1 over meters. So the units are the same on both sides. So it's correct, okay? And you can check it out as well. So if f is equal to 1 over t, then we have 1 over t squared here. So if you square both sides, you get 1 over t squared is going to be v squared over lambda squared. Right? So then what we can do is we swap that in. So it's be this is times cos gamma. So that's going to be, I'm going to sub in 1 over t squared for this. Sub in this for 1 over t squared, sorry. So you're going to have minus 4a pi squared v squared on lambda squared times cosine of gamma. Now what you might notice is that this, well, okay, I'll make it easy for you. I'm just going to rewrite this as factor out, not even factor out, I'm just going to show that it's v squared times this piece. But this piece is, what the hell, why is there a minus sign? Oh, shite. I'm so confused. I mean, it's minus 8. I'll be right back. Alright, it's okay, I didn't do anything wrong, I forgot. Yeah, when I did this, rewind the video, okay, there's a minus sign here. Yeah, I forgot about that. Perfect. So as you can see, the acceleration in the y direction is just v squared, velocity of the wave squared, times this, and this is just nothing but second derivative of y with respect to x. So okay, so as you can see, as we've shown, this acceleration in the y direction is equal to v squared times the rate of change of x of y with respect to x, and whatever. It's this constant times this. So we've got this relationship here, and we're very close to resembling this initial relationship. All we have to do is divide both sides by a v squared, so you're going to get 1 over v squared. And now, what we've done is we've shown, well, as we know, this relationship is going to always be proportional to this relationship, but we've got two constants which must be equal, because these are related equally, obviously. So this implies that mu over ft, that constant of proportionality, is equivalent to this one, so that's going to be equal to 1 over v squared. You could raise both sides to the power of -1, whatever, doesn't really matter. You get v squared equals tension over mu. And finally, v, velocity of your progressive wave, is equal to the square root of tension divided by your linear density. And that's where that equation comes from. I'm going to bed.